Good morning, everyone. We are just over the moon to pitch our scientific investigation to you all. My name is Tani, and this is
Belle, Maddie, Ainsley,
and today we present to you Magriculture. It's simulating gravity via magnetic fields to facilitate plant growth in microgravity. We want to utilize magnetism to manipulate the internal cell body of plant roots and observe the effects on plant development.
but first, let's take one small step back.
And one giant leap.
No. And look at why this experiment is so important. What's one of the principal culprits responsible for the greatest number of mission failures in the history of human exploration? Nutrition, or the lack thereof. There's simply no way of dodging around this imminent impediment to space exploration. The ability to grow fresh, nutritious fruit and vegetables with the utmost refined speed, effectiveness, and nutrition is of paramount importance.
However, there is a major obstacle in the way. Studies have found that in a microgravity environment like the ISS, plants are unable to identify which way is up and which way is down, and therefore they send their roots in every direction. Why is this? At a plant's root cap cells, gravity imbalance are detected. Inside the cells are gravity-sensing organelles called statoliths, or microscopic grains of starch. Direction of growth is determined by how these grains settle within the cell. On Earth, thanks to gravity, statoliths settle at the bottom of the cell. A hormone called auxin relays this to the rest of the plant, indicating to the plant, this way is down, so send the roots this way. Subtracting gravity from the equation, what do we find? In microgravity, they float around within the cytoplasm, and without gravity, they can't settle, leaving the plant essentially blind. In the image, we can see that the roots grew in all directions, in some cases even extending above the soil. This can critically affect the yield of the plant as it doesn't acquire its nutrients effectively.
This brings us to our experiment. We want to investigate the simulation of gravity from plants on the ISS, triggering their native gravitropism, or gravity-sensing mechanisms. We'll do this by using magnetic fields. This builds on past experiments, which found that 1, statoliths become displaced in microgravity, and 2, that they react to a magnetic field. This is due to a quality of starch being the predominant component of statoliths, called diamagnetism. This essentially means that starch is repelled by magnets, by a magnetic force. Hence, we want to observe the effects on plant development in hydrogravity when subject to a magnetic field. We hypothesized that by artificially directing statoliths into position, the plant roots will grow in one uniform direction, reaching nutrients faster and beneficially affecting the plant. As for what plant we'll be using, we want to use pea shoot seedlings. Pea shoots are durable, fast-growing, and contain a variety of nutrients and minerals, making them a key candidate for future long-duration space travel. We intend to measure the speed and angle at which the plant grows, direction of root growth, and statolith arrangement.
If we're able to stimulate plant growth and better understand the process of gravitropism in microgravity, this will have far-reaching effects on future space travel. The experiment, if successful, may open a gateway to increased crop yield and effectiveness under microgravity conditions. When space travel leaves Earth's lower orbit, vitamin pills and packaged food simply won't cut it. Pre-made pills are finite, non-renewable, degradable, and therefore unsustainable. We need to develop a fast, efficient way of growing food crop, which utilizes their natural growth tendencies and maximizes nutritional value to ensure the astronaut's survival on such trips. Furthermore, this may have implications for further space travel when growing food in low-gravity atmospheres, such as on low-mass moons. Where in space, the magnitude of the gravitational vector is near zero. The replication of this phenomenon on Earth instead constantly changes the direction of the vector, produces outputs that have a subtle but significant difference.
Improved nutrition means improved astronaut health. Perhaps one of the most common and deleterious consequences of space travel is that of bone density loss. It is estimated that in the zero-gravity environment of space, astronauts face a 1 to 2% loss in bone density each month. While a minor concern for short-duration space flights, this becomes exponentially more threatening for long-duration flights. For example, 3 to 4 year trips to Mars. How will maximizing the effectiveness and sustainability of agricultural growth on the ISS affect this? Well, maintaining a nutrient-dense diet is essential to combating the degradation of bones and muscles. For instance, the vitamins D, K, and C all contribute to the synthesization of calcium into bone. By maximizing the yield and growth speed of food on spacecraft, the likelihood of acute bone density loss is greatly reduced. Knowing how to grow various plants in microgravity also enhances dietary variety.
The process. To execute our investigation, we have devised a simple yet effective design. It consists of a compact plastic acrylic box to house the experiment. The pea seedlings will be grown in a culture containing a nutrient pillar. These have been used on the ISS multiple times in growing plants and vegetables, and are essentially packages of nutrient-dense soil with control release, fertilizer, and water. The pillar will receive 3 seeds as a barrier against germination failure. On either side of the seedlings will be 2 strong bar magnets. These will provide the magnetic force to simulate the gravity. Now what you've all been waiting for, the science. Why will this experiment work? Well, as Bill mentioned previously, the gravity-sensing satellites are diamagnetic. This means that they become magnetized 180 degrees to the magnetic field. What does this mean? So if this is the north pole of the magnet, the starch granules will be magnetized similarly. So if this is north, the one closest will be north. Basically that means that no matter the orientation of the magnet, they will be repelled. So what this means is that they want to push towards the weaker field lines of the magnet because they're diamagnetic.
With the 2 magnets above them, the statoliths, otherwise floating, are pushed to the bottom of their cell. This sends a signal to the plant saying that this is where the bottom is and to send your roots growing this way.
This imitates the regular behavior of statoliths under Earth's gravitational field, pushes them down with gravity. Here in the diagram we see that they are pushed down because of the magnetic field lines.
We will measure a variety of factors such as the direction of root growth and cell disposition, and this in relation to the germination speed and the angle of growth. At the end of the experiment, we will be able to freeze dry a sample of the root containing the root cap cells and then bring it back to Earth for examination. Our control will be the same plant species growing in microgravity but without external influence. The expected results for this experiment will be that the seedlings exposed to a magnetic field will have a noticeably faster germination time and higher germination success rate than the control, as can be seen in this graph. As for root growth, we will tabulate the results of how many roots grew in the correct downward direction above ground and to the side. We hypothesize that the experimental seedlings will have more roots oriented downwards.
As in any science experiment, complications are likely to occur, and we know that it's vital to have an airtight plan given such a predicament arises. A potential complication that might occur is in the preservation of the organic plant sample. Plant cells are more difficult to preserve than, say, bacterial cells, so there may be a possibility of something going wrong. This is easily remedied by simply using external observation as opposed to intrusive cell examination. While we intend to inspect the microscopic effects of the magnetic field, even if all goes wrong, we will be able to infer those results through the external examination of the plant's roots.
In summary, we will be investigating the effect of magnetic fields on gravitropism and microgravity. We want to identify and understand how a magnetic influence will affect the development of a plant suspended in microgravity. This builds on previous works investigating both statolith organization of microgravity and diamagnetism of statoliths. Through this, we attempt to further the efficiency and sustainability of space agriculture, thus having lasting effects on astronaut health and nutrition. Advancements in this field are essential for forthcoming long-duration space flights and flights to distant celestial bodies, and even in the far future, sustaining life on such planets.
Thank you for listening.